Hey everyone, my name is Tien. I work at Blockstack. Welcome to Blockstack Lunch and Learn on the Technical Computer. We presented Aaron Ringstein, who is one of our core engineer. This Lunch and Learn will be recorded. We're going to be publishing this afterwards to our different channels community. I have Jenny here, who is our digital community partner. We have a bunch of folks here from Blockstack HQ as well, and then we have more folks joining in from remote. So we have about maybe 13 participants right now. I think more might come in a little bit. Aaron, please feel free to start whenever. I think we will mute ourselves and we'll also turn off our video during the presentation, but we might turn it on again. We have during the questions and answer portion of this Lunch and Learn. Thanks everyone. Thanks for joining. Aaron, turn.
Okay, I think I needed to unmute myself before I started the screen share. So let's try this one more time. Okay, can people hear me and see this screen?
Yep.
Yes.
Okay, awesome. Cool. Hi, everyone. I'm Aaron Blankstein, one of the core engineers at Blockstack. I'm going to be talking to you today about version 2 of the Blockstack white paper, which was recently released. And in particular, I'm going to be covering mostly the blockchain section, which is kind of the section of the white paper that has changed the most. There's a lot of other material in the white paper as well that you can check out, and maybe we'll do another lunch and learn on. But that's mostly what I'll be talking about today. During the course of this presentation, feel free to pipe in and interrupt me. You might have to do that verbally because I'm remote, so I will not see any raised hands. So yeah, feel free to stop me at any time for questions. If it gets too excessive, I might start ignoring you, but yeah, cool. All right, so this first slide is a disclaimer about this talk. Yeah, so everybody should kind of briefly scan over this, digest it, internalize it, and then we'll move on to the actual content of the talk. Cool. Okay, so I think the way that I want to start is sort of the way that the white paper itself starts, which is kind of like motivating what Blockstack is trying to achieve in the world, what our blockchain itself does, things like that. So I'll start the same way. So when you look at like the internet that we have today and how people actually use it, one of the things that's like most pervasive about the way people interact with the internet is that cloud computing really dominates. What cloud computing is, it's a lot of different things to a lot of different people, but for the most part, what cloud computing is it's a model where our computers, our phones, tablets, smart light bulbs, whatever, these computing devices aren't really responsible for like the core functionality that they're implementing. That like core business logic, that core functionality is actually done in the cloud, which usually means it's done in some server in California, operated by whatever company you're using the service of. And that company is like sort of choosing how the application behaves sort of live. It's a lot of examples of like cloud computing apps. So if you think about how, say, Twitter works, it's sort of classically cloud computing, right? I write a tweet, I send my tweet off to Twitter. Twitter processes my data, decides who else should get to see it and when, and then sort of sends that information back to them. Cloud computing is very powerful. It's taken sort of the world by storm, and it's a very easy programming model for people to use. However, cloud computing is actually terrible. As you can see, this cloud that we've sent all of our data to is actually just like striking us all with lightning bolts, I guess, somewhat metaphorically. So the reason cloud computing is kind of a terrible model and people are sort of starting to recognize that it's a terrible model is because like we're giving all of this data to these applications. These applications are hoarding our data. They actually, like these applications they're actually storing more data about us than really anyone has ever stored information about anyone in the history of the world. It's actually kind of unfathomable how much information these cloud computing companies have. So like one way to think about it is at the point in time that we're at today, like it is not even a surprise, like it barely registers as an event when there is something like a data leak of 100 million or 200 million users, right? Like that's like not a huge deal. It's something that's totally understandable. If you had told someone that that would be like a regular occurrence 20, 30 years ago, I think they would be like totally shocked at just sort of like the scale of data that these companies are hoarding and also leaking to the public at large. Okay, so if cloud computing is so terrible, what do we do about it? The answer is Blockstack. So so I think that like the sort of the model that Blockstack takes, which is sort of we view as an alternative to the cloud computing model, is actually a model where you have sort of decentralized applications where rather than the application storing and managing all of the data on the user's behalf, the user is storing data in a private data locker of their choosing. They sort of selectively reveal that data to applications and to other users of those same applications. So how this works is like Blockstack provides an API and a stack that provides the necessary functionality to build these kinds of decentralized applications. So the first thing that you need if you're going to build a decentralized application is like you need this mechanism for private data lockers. So here we have all of these users and they're storing their information in Gaia hubs. Gaia is Blockstack's protocol for these private data lockers. Okay, that works pretty well, but at some point, users, they want to be able to like share data with each other, right? So if we're only interacting with these private data lockers, we don't have any ability to share data with other users, okay? So how do we solve that problem? So the way that we do that is actually through the Blockstack naming system. So we have a method for determining like the sort of unique names for users and mapping those unique names to Gaia hubs. So that if like two users, Alice and Bob here, wanted to like share data through one of their Gaia hubs, BNS would be like a method for routing that information between them. And then on top of all of this, we have the Stacks blockchain, which allows people to register names on BNS and also transfer stacks between one another. And all of this is implemented and works today. Okay, so it works. So then why do we have a version 2? Like what is the Blockstack white paper version 2 describing? So I think that like the primary thing going on here is that all of that today works on the Bitcoin blockchain, right? So a lot of those, all of those transactions, BNS transactions, Stacks transactions, all of those are encoded using the op return field of Bitcoin transactions. And what that means is that name transfers, renewals, registrations, even if those registrations are paid for using Stacks, they actually require a Bitcoin transaction fee. Because you're building up a Bitcoin transaction, you want a Bitcoin miner to include it in a block. So that means Bitcoin miners are profiting from all of this activity on the Blockstack network. All of this functionality is actually like trying to share network bandwidth with Bitcoin, and it depends on like technological development of the Bitcoin blockchain, which is like a very sort of slow to change blockchain. And it's also a blockchain that's like not really built for this, right? Like it would be hard to imagine that like the Bitcoin blockchain is going to implement changes that would improve functionality specifically for the Blockstack network. And so in addition to that, there's some like limitations of the way that, say, Stacks and BNS names are currently implemented. So one is that the Stacks blockchain today doesn't have smart contracts, which means there's no ability for developers or participants in the network to extend the network's functionality without hard forks, things like trying to organize hard fork. The other thing is that because there's no smart contracts, you have no real ability to have like programmatic control of BNS names or Stacks tokens. Things like escrow, they're not possible with BNS names or Stacks tokens today. So we have all of these limitations, and we also have these concerns where basically we're like sharing a network and technological bandwidth with the Bitcoin blockchain. Both of those are negative things, and we think that like with version 2 of the Stacks blockchain, we can improve across like basically all of these dimensions. All right. So what are we trying to build ultimately with the Stacks blockchain version 2? So like one of the sort of chief design decisions we made is that we actually want open membership mining with peer-to-peer network propagation. So what open membership mining means is that basically at any point in time, anyone out in the network can participate as a miner. This is in contrast to closed membership blockchains where, you know, there's either some like out-of-band election protocol or just like an explicitly closed set of people that are allowed to participate as miners or builders or producers of blocks in those blockchains. The second thing that we wanted to achieve is that with our mining protocol and consensus algorithm, we wanted to have the ability to have a tunable proof system where basically given a parameter, we can tune a mix of proof of work and proof of burn to actually secure the consensus algorithm of our blockchain. And I'll talk in more detail about how that sort of works in a later slide. The next aspect of our blockchain is that actually at any given point in time, each block has like a single leader and has kind of like an epoch over which they're leading. So this is a system that we call single leader election. This uses sortition to select that leader. Leaders are elected through Bitcoin blocks. So a new leader, potentially a new leader, is elected about every 10 minutes. Those blocks are confirmed at sort of roughly a speed equivalent to Bitcoin. Our transaction throughput, because of how we're doing peer-to-peer network propagation, because we have open membership mining, and because we're doing this election every 10 minutes, we end up with transaction throughput sort of roughly similar to Bitcoin, meaning that we're sort of like operating with the same constraints as, say, the Bitcoin network is when we're tuning how much bandwidth we want to support, things like that. This election system ultimately allows us to build a system where transaction fees are actually no longer paid in Bitcoin, though, because in this system, there will actually be like stacks blocks. So stacks transactions, they're all packaged together in stacks blocks, and you have like a stacks miner. So they'll be accepting fees in stacks rather than in Bitcoin. And finally, the stacked blockchain v2 is going to add support for our smart contracting language called Clarity, which I'll also talk a little bit about during this presentation. Okay, so the first thing I want to do is talk about the consensus protocol for Stacks v2. I'll talk about how we do single leader election, how the tunable proof system works, and also a little bit about fork selection using the longest valid chain. Okay, so when any given node is elected as a leader and is selected to build basically the next block of the Stacks blockchain, they operate in a pretty straightforward way. So when a leader is selected, they're responsible for choosing basically which chain tip they're going to be building off of. So as the blockchain is moving along, they get to choose like sort of where they're attaching, like where their block is going to go. They choose ultimately which transactions they're going to include in the current block. That's essentially a greedy choice by the miner. And the greediest choice is usually to choose by fee rate. And then the leader is responsible for broadcasting all of those choices to the network. And that's done through our peer-to-peer protocol. And basically what that means is that you have to broadcast your block or any sort of streamed portions of that block to the network at large. These operations are like not unusual for a blockchain. They're pretty much the essential functions for any given blockchain. And how these things are implemented basically tells you like how a blockchain ultimately works. So cool. So for this talk, I'm going to focus on that first item, choosing which chain to build off of, choosing which transactions to include in the current block, and broadcasting those choices to the network. We do in pretty standard ways, or the design calls for doing them in pretty standard ways. So I'll talk mostly about the first. Okay, so when Stacks leaders are participating in the network, basically when they do their proof of work or proof of burn, they commit to the chain tip with basically a hash where they say, okay, this is the chain tip that I'm going to be working off of, and my proof of work and proof of burn are only valid if I'm actually building off of that chain tip in particular. This is analogous to how proof of work functions in the Bitcoin blockchain, where miners are basically searching for a nonce that makes their block hash to an appropriate hash, and their block is got a pointer to the previous chain tip. So like that functions as their commitment to the chain tip that they're working off of. Okay, so once a leader has been elected, the leader is able to start including transactions in their block and stream them out to the network. So a leader could basically say like, hey, I'm going to take these 5 transactions, link them together in this order, and then broadcast them out to the network. And the network can verify that that's all true because everybody in the network has the same view of who the current leader is. Okay. So once my epoch finishes, a next leader will begin building the sort of next section of the blockchain. And if you want the blockchain to function sort of well, in an ideal world, the next leader should choose to build off of the last block that they've seen. So if you're streaming out these transactions, the next leader should say, okay, what's the latest transaction from the previous leader? I'm going to build my block off of that latest transaction. But what if that last transaction was a super high value transaction? Like it had a very, very high fee. Well, then like a greedy leader might say, actually, I want to build off of the transaction prior to that one. And that way I'll be able to include that like high value transaction in my block. And then I'll get the fee rewards for including that transaction and not the previous leader. So this is a problem because you ultimately want your blockchain to make progress. But if you have high value transactions and leaders are able to choose where in the chain they're building off of, you might have leaders that are like continuously fighting over these high value transactions, and they might try to split the previous leader's block. So to deal with this, we actually have two solutions. One is that for transactions that are streamed in this way and could possibly be split off by a subsequent leader, fees are split 40% and 60% between the leader that announces that transaction and then the following leader. And what this means is that the following leader is actually more incentivized to confirm that transaction rather than try to reorganize it and announce it themselves, because they get more rewards from confirming rather than announcing. So that's the first solution. The second solution is that leaders can actually hard commit certain transactions before beginning the process of streaming out the rest of their block. And they do this by including those transactions in the hash that they announce with their proof of work or proof of burn. And that makes it so that these transactions cannot actually be split off by a subsequent leader. And so you'd expect, because of this like 40-60 split, that leaders will mostly be incentivized to try and commit as many transactions as they can using this second process. Because if they use that second process, they actually get all of the transaction fees. All right. So that's how a leader sort of operates once they've been elected. But how do we actually perform leader election? So the way that leader election works is there's two components at work. So one is leaders or candidates participate in the consensus algorithm by burning Bitcoin or performing some amount of work. By doing either of those things, they get a score for a particular election block, and that score is used to sort of like rank these leaders. The second component that's happening, the second thing that's happening, is that there's a cryptographically random process, which is selecting a leader weighted by those scores. So if my score is 2 times higher than someone else's, I have a 2 times higher chance of being the next leader, but it's not like a deterministic process. Well, it actually is, but there's a cryptographically random process happening that's selecting between the two of us. All of these components are committed to the burn chain, which is Bitcoin, so that you can, at any point in time, determine who the leader is based on reading the burn chain exclusively. All right. So let's look at an example of 3 candidates attempting to lead the next block, basically this block number 4 here. So candidate A burns 1 Bitcoin, performs 25% of the work of the group of 3, and they're committing to building off of chain tip number 2. Candidate B burns 1 Bitcoin as well, but performs twice as much work. Candidate C burns twice as much Bitcoin, but performs 25% work as well. So basically the score that each of these candidates is going to get is going to depend on the tunable work parameter, which is not defined in the white paper or in our SIPs. It's sort of left as an open parameter. But in this example, let's just assume it's 50-50, so that like you get 50% or 50% of your score is composed of your burning percentage, and 50% of your score is composed of your work percentage. So like here, candidates B and C are like equally have equal scores, and candidate A has a slightly lower score than the two of them. Based on these scores, you get each candidate gets a sortition range, which is a range from 0 to 1, indicating like what corresponding to like what percentage chance that candidate has of being selected. So if the cryptographic random process spits out a random number that's 0.8, then candidate C will be selected. If it spits out one that's like 0.3, then candidate B would be selected. If it spits out one between 0 and 0.25, candidate A would be selected. So let's see how this would work. So let's see. So let's say we had a random sortition value of 0.55. That falls into candidate B's range. So candidate B would be selected for the next block. Now candidate B committed to working off of chain tip number 3. So that means that they're going to be extending this blockchain with this block B here. Okay, what if the random sortition value was 0.15? Then in that case, candidate A would actually be selected to lead the next block. But candidate A committed to chain tip number 2. So what candidate A is actually doing is they're building this next block. Instead of building it off of the block number 3 up there, they've actually created a new blockchain here of length 3. Oh no, now we actually have 2 chains. So how do we resolve this dilemma? Yeah, this is actually the part of our consensus algorithm that's doing chain selection. So how do we select between 2 candidate chains? The answer is fairly straightforward. So if you have 2 candidate chains, you select the one with the most blocks. So that's pretty straightforward. It's basically, for any candidate chain, you can look at the history of elections in the burn chain, see how many leaders are committing to a particular chain, and just sort of weight the chain with the most leaders as the winning chain. In the event of a tie, a properly functioning node should select one of these chains randomly. Okay, so what would happen in the example from before, where we had 2 candidate chains of length 3? So when the next leader is elected, if that leader is honest, they will select one of these forks, either fork A or fork B, at random. This will create a length 4 chain, and then a subsequent leader, if they're honest, will see and follow that fork, because that fork is the longest and therefore the best. And so eventually we'll get a chain that dominates, and the other fork will sort of die off. All right. So what does this consensus algorithm, what does this whole process give us? Ultimately, it gives us a open membership, a blockchain with open membership mining, where transactions and blocks are propagated through a peer-to-peer network. Anyone out there can become a miner. You don't actually even need mining hardware to participate because you can just burn a cryptocurrency to participate. The security of this blockchain, like almost any open membership mining blockchain, ultimately is going to depend on the mining interest. So the more miners or the more mining power that is confirming a given transaction, the more secure that transaction is. Mining in the system is done through tunable proofs, where you have a variable T that tunes a mixture between proof of work and proof of burn. The confirmation speed that you get from this network is roughly equivalent to Bitcoin. Though if your transaction is sort of streamed out by the current leader, you get an instantaneous promise from that leader that the transaction will be included in the next block. So it's a little bit different than the concept of confirmation in Bitcoin, but you get some sort of instantaneous guarantees. And ultimately, the transaction throughput would be roughly similar to Bitcoin. Okay. Cool.
I have a question.
Yes,
If you want to pause,
go for it.
take them at the end. So someone asked me, it goes a little bit back to picking the leader. Is someone asked me where that information gets stored, and I didn't know. I know I'm a technical person, so I don't know if that question even makes sense.
Sure. So there's a couple of places where information is getting stored. So one is when you're getting elected to be a leader, that information is stored on the Burn chain, the Bitcoin blockchain. Basically, when you are submitting your candidacy for election, the way that you're doing that is you're burning Bitcoin through a specially formatted transaction on the Bitcoin blockchain, and announcing things like your public key and your commitment to the Stacks block that you're going to be building off of. That goes on the Bitcoin blockchain. The actual Stacks block itself is not on the Bitcoin blockchain. That's propagated just through our network.
Okay, yeah, that makes sense.
Cool.
I have a quick question.
Yep.
The line that says the security of the blockchain depends on the mining interests. So does that imply that the greater the interest in mining, the more secure the chain is?
Yes.
Okay, and so if we don't garner the interest in mining, does that mean the blockchain is less secure or just not as secure as it could be?
Yeah, it would be less secure because, yeah, ultimately, if there's no mining interest, what that means is that anybody could, say, burn some like very small amount of Bitcoin and lead many blocks in a row. And if you lead many, many blocks in a row, you can sort of reorganize and fork the blockchain kind of at will.
And so is the concept that anyone can become a miner sort of, like right now there's a lot of interest in general Bitcoin mining where there's groups of miners and things like that, so that it sounds like the accessibility to mining is being reduced in other blockchains and we're trying to expand it?
Yeah, so we're trying to, one of the things that Proof of Burn does is it reduces the barrier to entry for participating in as a miner, because you don't need to buy mining hardware.
Yeah. Okay, cool, thanks.
Cool. Okay, so now this talk is going to take a sharp transition and talk about one of the cool things that will be enabled by version 2 of the Stacks blockchain, which is our smart contracting language, Clarity. So Clarity is a way for people to extend the functionality of the Stacks blockchain without initiating a hard fork. And they do this by defining smart contracts that other people can then interact with, or they can interact with themselves. Our language for writing these smart contracts is called Clarity. It has a number of interesting features. One is that it's a non-Turing complete language, which I'll talk more about like why that is and sort of what that means later on. Clarity is an interpreted language rather than compiled, which is different than most other smart contracting languages. Clarity is it's implemented as a variant of Lisp, which means that if you're reading Clarity code, you should expect to be reading a lot of parentheses during your time there, or if you're writing them, expect to use your parentheses key. Clarity smart contracts themselves, basically what they're trying to do is they define maps of data which are under the control of that particular smart contract. And then they define functions that are either private to the contract itself, so they can only be called by other functions within the same smart contract, or functions that are callable from other contracts or by broadcasting a Stacks transaction. One of the neat things about Clarity, and sort of a direct consequence of the fact that it's non-Turing complete, is that it allows for many different kinds of static analyses. So it allows for analyses that will determine whether or not types in a smart contract have been used correctly, so that if you have a map of data which is mapping, say, integers to Booleans, Clarity's static analyzer will make sure that you're like not trying to store an integer where a Boolean is actually expected, things like that. This type checker will actually also enforce that you're properly handling values that could potentially be null, things like that. Static analysis can also determine the complete set of possible code paths for any transaction, and not just the complete set of possible code paths, but also the complete set of other smart contracts that could ever be called by any given transaction, which is a pretty cool feature. Finally, static analysis can also determine for any given transaction what the runtime cost for that transaction will be, which is pretty useful for blockchains where miners are actually responsible for executing transactions. So they can know, without executing the transaction itself, they can know a priori how expensive it will be to actually run that and execute that transaction. All right. So the first design decision I want to talk a little bit about the motivation behind and thinking about is the fact that Clarity is an interpreted language. So most other smart contracting languages are compiled. Oh, there's a typo there. But most other smart contracting languages are compiled, whereas Clarity is interpreted. So what this means is that the actual code that programmers are writing, that code itself, or like a representation of that code, is ultimately what is published on the blockchain. In other languages where you have a compiler, the compiler is translating that code into something sort of like an assembly language, and then publishing that assembly language on the blockchain. And the hope is that like your compiler, if it's implemented correctly, that assembly code is expressing the same exact thing that the code you wrote expresses. An interpreter doesn't have that problem because the code you wrote is the code that's getting published in the blockchain. And the reason we do this is because we believe that compilers that have bugs can introduce like a really, really terrible failure scenario for blockchains in particular. And to see this, let's I just want to run through like a quick example of like what a compiler bug looks like. So in a perfect world, our compilers perfectly translate source code into assembly code, which means that for any input to your source code program, if it outputs something, like outputs Y, the code, the assembly code produced by the compiler would perform the exact same, right? It would do the exact same thing. Like for any input, it would produce the same output, right? That's the hope. But unfortunately, this isn't always the case. Compilers are programs. Compilers are programs written by people. People are fallible. Programs ultimately always have bugs. The tricky thing about a compiler bug, though, is that if you have a compiler bug, it affects only the assembly output, right? So you could have correct source code. So like you have some smart contract author that is like very diligently ensured that his smart contract code is implemented correctly. He's implemented tests on it, all sorts of things. And he's done a perfect job of writing his source code for his smart contract. However, once it hit the compiler, the assembly code produced, that's the only code that has the bug, right? Like the programmer has no way of scrutinizing that code because that's not the code they're writing. So if you had one of these compiler bugs and it produces this buggy assembly code, and then that assembly code is published on the blockchain, other people are now able to transact with your like buggy code, and you know that could be catastrophic for your smart contract. Now, in the event that like you have, in the event that you have one of these compiler bugs, the question is, as like a community, as a network, like how do you recover from this? So one of the obvious first things you do is you say, okay, we patch the compiler. And once we patch the compiler, because this is like a problem in something that maybe we include in the trusted set for our blockchain, maybe we should conduct a hard fork to try and fix this so that contracts which were published with this buggy compiler, we can fix them and like undo any buggy transactions. But this leads to a lot of like really scary questions. Like one is, how do you recover the source code? It's not, generally speaking, possible to recover source code from assembly, or it's not always possible. And so at that point, you have to say, well, we kind of have to trust programmers to supply us with their source code, or like, yeah, it's really tricky. So if you like live in this world where what you're trying to say is that like what lives on the blockchain is the ground truth, ultimately, you're put in this position where you have a compiler, which is part of your trusted set, that is actually mangling your ground truth, which is kind of scary. But using an interpreted language basically just eliminates this whole class of bugs. Like you don't have to think about these problems at all, because if you had a bug in your interpreter, that's equivalent to a bug in the blockchain code itself. And it's very easy to say like, oh, we have this like buggy blockchain node, we have buggy blockchain software, we can patch that and then initiate a fork that would probably be much less contentious. Okay, so that's why we went with interpreted rather than compiled. Okay, so the next interesting thing about Clarity is that it's non-Turing complete. So this is interesting because like normal programming languages are actually usually Turing complete. What Turing complete means is that the programming language is basically able to represent any computable program. So like basically anything that you would normally think of a computer being able to do, you could represent using a Turing complete programming language. Turing completeness means some other things too. So it means that like analyzing what a program will do without executing that program. This is called static analysis. for general properties is often impossible. So there's like a limited set of static analysis that you can do on a Turing-complete program. But answering general questions is not possible. It's equivalent to various impossible problems that have been proven impossible. Things like decidability. Specifically, the thing you can't do with Turing completeness is know whether or not an arbitrary program will ever finish running or how long it would take to run. That's the decidability problem. So Clarity, rather than being Turing complete, like we wanted our static analyzer to be able to do lots of things, right? And so we said, we'll make Clarity a non-Turing complete language so that we can support many different kinds of static analysis, not just static analysis that we can think of today as being useful, like the cost of running any function, but also like many sort of future kinds of static analysis that could be implemented somewhat directly compared to other kinds of programming languages. So for Clarity, a static analyzer can actually determine things like the cost of running a smart contract function, whether or not a given function is correctly typed without requiring explicit type annotation of things like returns. It can also determine the complete set of possible execution paths for a program. And all of that opens the door to many other kinds of advanced analysis. So if you wanted to have like a proof checker, if you wanted to build a proof checker where you could say like, okay, here are some like conditions that my smart contract should never violate, you can kind of check that those conditions are actually met programmatically or automatically using automatic proof checker. And that all of that is aided by the fact that Clarity is a non-Turing complete. Cool. So some of the like interesting consequences of Clarity being non-Turing complete are that a lot of like very standard programming constructs basically don't exist or work the same way. So programming in Clarity is a little different than programming in like a normal Lisp. So there's no loops, no general purpose loops, and there's no recursion. So you can't use recursion to implement loops. The only way that you can iterate over things is you can only iterate over fixed size lists. So we give you functions like map, filter, fold, but you can only apply those things to lists that are basically fixed in size or have maximum length. The data model for a Clarity smart contract is data maps, not database. So map is like key value store. And so you can't do things like SQL queries or like scans across a data structure like that. You can only do like key value operations like get and finally, in Clarity, there's no support for dynamic dispatch or other kinds of dynamism in the language, or functional dynamism. So you can't do things with anonymous functions or treat functions as objects, things like that. Cool. Yeah. So what does Clarity ultimately actually look like? It's going to look a lot like Lisp. So Clarity is a Lisp variant. Lisp was originally specified in 1958. It's a very old language, somewhat stupid at the time. One of the really nice things about implementing Clarity in Lisp is that it's very easy to implement Lisp interpreters, right? So the language itself doesn't have very complex grammar, complex lexing structure, any of those things. And the nice thing about that for developers of smart contracts is that you can have a lot of assurance about how the interpreter is going to interpret the program, right? Like the source code for the Clarity VM is not some massive improvement that it's sort of easy to analyze. So that's sort of a nice side benefit of Lisp. The other benefit is that generally speaking in Lisp, you have a lot of insight into what is happening at any given time. And it's very clear in the writing, if you sit on Lisp, like what is going on, right? It's a functional language, so it's very clear. Yeah, so anyways, here we have an example of a function in Clarity that's attempting to transfer a simple balance from one user to another. And basically the way that it works is it's fetching the current transaction sender's balance. It checks that the balance is greater than the amount being told to send. It also checks that the amount that you're trying to send is greater than 0. If either of those things are not the case, it returns an error, and otherwise it updates the data map that is actually tracking the account balances for any given account. Yep. And that pretty much is it for Clarity. Yeah, so some of the topics, other topics covered in the white paper that didn't discuss today, that are really rich and great topics in their own right. Things like Gaia, which is a storage protocol, authentication protocol, and some examples of authenticators used in that protocol. How things in our system like subdomains and subdomain registrar work, and also things like all those topics in the white paper. I didn't talk about them here because just covering the topics that I did kind of at a high level took up a lot of time. So if you're interested in those topics, I recommend checking out the white paper. In fact, I recommend checking out the white paper anyways, and also our SIP and source code, because ultimately those things probably do a much better job describing what's going on than I do. And there's things I've missed and all sorts of stuff like that. And now we get to the questions slide, which I'm just going to leave up here and then wait for you to ask me questions. Thanks for listening so far.
Thanks, Aaron. We have about 6 minutes left, so I don't know if anyone wants to have, if you have a question, maybe just, actually, you don't have to turn on your camera, actually. Yeah, just feel free to just jump in and ask questions. If you're muted for some reason and you're not able to unmute yourself, let me know as well by sending a message via Slack. Sorry, not via Slack, via the Zoom chat.
Yes, hello.
Via Slack,
Friedke.
the chat. I'm sorry?
Hello, this is Friedke.
Hi.
I have a question. I was missing a bit in the white paper motivation why proof of work is needed and how the proof of work is different than on other blockchains.
Yeah, so I think that one of the motivations for proof of work is that it provides a kind of path towards developing our own proof of work mining interest, separate from Bitcoin's, in the event that, say, the Bitcoin blockchain has like a massive reduction in interest, or for whatever reason, the Bitcoin blockchain becomes infeasible for us to continue to operate on top of. It like provides an avenue for us to sort of scale up a different security mechanism.
And the virtual chain is not a good solution.
Right. So yeah. So the virtual chain essentially does not exist anymore in the Stacks v2.
Because
the virtual chain suffers from the same kinds of problems detailed with basically the problems with Bitcoin, which is that it pins your many functionalities of your blockchain to both the technology and also the transaction fees of another blockchain.
So the Blockstack chain, the main version 2, the main improvement is having smart contracts.
That's, yes. So that's the biggest new, I think, like, I guess if you were to call it a feature, yeah, that's probably the biggest new feature. But I think
couldn't the BNS move to like Ethereum or another blockchain that supports smart contracts if that was a goal to achieve?
Right, but I think that sort of goes back to the other point, which is that we don't want the Stacks blockchain to be reliant on another blockchain for either transaction fees or the technology of the blockchain itself. Like, we don't want to be sharing network space with like other kinds of transactions that are basically not BNS or Stacks related.
And then from a application developer or from a business perspective, what is the main advantage to choose the Blockstack chain over Ethereum or EOS? Or so what are properties that other chains do not have, where as a business person would say, I want to run my application on the Blockstack chain?
Well, so I would say that our blockchain is different across like a wide array of features. So one is, I would say, the smart contracting system is quite different, and in a sense, like, can give a smart contract writer basically more assurance about how their smart contracts are functioning once deployed. So that's sort of one avenue. I'd say the ways in which the consensus algorithm differ are sort of more broad, where, you know, we have open membership mining, which is different than a number of competing blockchains today. The other is that proof of burn mining allows like a wider set of people to participate because you don't need mining hardware in order to participate as a member. And then finally, I would say that the Blockstack SDKs and sort of ecosystem that we have for building applications, I think is very good and differentiates us from other blockchains.
But that they are not really linked to the blockchain, I would say, the two SDKs.
I mean, I think that they ultimately are, right? Because you have BNS, and then ultimately once smart contracting goes live and the support for that is introduced into the SDKs as well, ultimately those are interacting with the blockchain.
Yeah, I see the possibility that the SDKs can also include other blockchains, but so that application developers that who would like to use a blockchain with free transactions, for example, because they're not that valuable, they should be able to use it as well.
So it's 1 o'clock. This is the amount of time that we scheduled for this Lunch and Learn session. If you have any other questions, Jenny, where should they? Do you have an idea of like where people can submit questions? Maybe on the forum or something like that.
On the forum is probably best.
Yeah.
Community Slack. Also open forum for her.
Yeah, and then so we have the recording of this Lunch and Learn. We'll be posting it up with with Erin's presentation as well on the forum, and then just maybe you can reply onto that if you have any further questions, and we'll do our best to answer them as they come in. Thank you everyone for your time and for participating. Erin, thank you so much for giving this Lunch and Learn. Thank you for that. And we'll see if we can schedule the future Lunch and Learn on the other sections of version 2 of our token white paper. Thank you everyone for coming.
Yep, thanks everyone.